Hello and welcome. I hope you've had a lovely Easter, and it's my pleasure to welcome you to this meeting of the Hartford Astronomy Group. Well, I'm really delighted to see so many people here on Zoom, and also lots of you down at the university. I can see from the applications that we've had that we've got people from all over the country with us today, people as far away as the Humberside, Guildford, London, Bradford, New Haven. So wherever you heard of us, well done, and it's a pleasure to welcome you to the meeting. The format of the meeting is I shall give you a few announcements about behaviour. So those of you at the university, please make sure that your phones are switched to mute. And I'm sure you've probably discovered where the toilets are, but if you haven't, they're just outside the door that you came in. And for the people on Zoom, if I could ask you to keep on mute, keep your hands away from the space bar, because that will turn your microphones on again. And we don't want that to happen. The other thing I should do is to say that we're going to record the meeting with the permission of the speaker. Okay, I believe they're also recording it down at the university as a backup. The format, as I started to say earlier, is that after these short announcements, I will be passing you over to Martin Weston, our Vice Chairman, who's going to tell you about some of the wonderful things in the sky that you can look for. I'm sure he can have some lovely photographs to share with us. After Martin is finished, he's going to pass back to me, and I will then pass over to Jerry, who's going to introduce tonight's speaker. We're really pleased that Andrew's been able to come down and talk to us, so I'll leave the introductions there to Jerry. There will be an opportunity for you to ask questions. Now, those of you down at the university, you will be able to ask your questions direct. So just give a moment or two for somebody to bring a microphone to you so that those of us on Zoom can hear what the question is. For those of us on Zoom, if you have a question to put to the speaker, if you could type it into the chat box, then that can be read out so that everybody can hear it. We will then come back to myself because I've got a few announcements to make about some events coming along. So if you could bear with me at the end of the talk just for about another 5 minutes, and then that will conclude the meeting. We will aim to finish around about 9:30. For those of you on Zoom, we can continue a little bit longer chatting away off the record, so we won't be recording that. So that's all I wanted to say as the introduction. So I'm now going to pass you over to Martin Weston, who's going to share some of the night sky with us. So over to you, Martin.
Good evening, everybody. Good evening. Thanks for turning up on this rather dismal evening, but summer is not far, I'm sure. I'm just going to give a brief little chat today, a few items that I found that might be of interest to you. Can start my presentation. So the first, can you see that okay? Yeah, good. So I don't know if any of you have heard of JUICE. It's the new European Space Agency project, and it stands for Jupiter something. Icy moons, yes. Yeah, it's actually in the next slide. So there's just a nice picture of the Ariane rocket taking off, which I think is on the 15th. Let's go to the next slide because all the information's on there. There we are, Icy Moon Explorer. I should have just gone to that, shouldn't I?
Cool.
So launch, if all goes according to plan, will be tomorrow. So, and it's going to be live. There's a little bit of information on the bottom there about where you can watch it if you want. If anybody wants that information later on, I can certainly put it on get Alan to put it on the website, or I can give it to you directly. So, yeah, the interest obviously about the moons of Jupiter are the fact that some of them have liquid water under the ice that surrounds them, and the idea of this is to try and work out the suitability for life on these moons. So I'll put a bit of information there. So the main interest would be Ganymede, Callisto and Europa. So there's some remote sensing and geophysical in situ instruments being launched with the probe. So that's obviously going to take a little while to get there. So, but it's just exciting to know that's leaving and it's on its way. So again, taking off an Ariane 5 rocket tomorrow, and there is the live information here, 13:45 on 13th of April. So if you get a chance, please watch that. I'm sure it'll be very interesting. Right, so just what's in the sky at the moment. Well,
just want to mention that 17th of April Starship launch test.
Yeah, we'll do. So, quick bit of information from the desk. SpaceX Starship orbital launch 17th of April, so something else to watch out for. So SpaceX, or Elon Musk, isn't it? SpaceX. Right, so what's in the night sky at the moment? Well, I just want to mention Mercury because it's not always easy to see. It's very close to the sun, as you all probably know, but it's quite viewable at the moment, especially in the evening, just as the sun goes down. Obviously, be careful when the sun goes down that you're not, make sure the sun has gone down, you're not looking directly at the sun. So I've put a bit of information about where you can find that there. The thing about, it's going to reach its highest point, I think, today or yesterday, I can't remember now, but it'll still be visible. But as it moves round, obviously, it becomes more crescent. So it's not presenting, it's almost like a 2/3 disk at the moment. So as it comes round, you'll be able to see more, it will just become less bright and you'll become more crescent. But that's, and Venus is very visible at the moment as well. They're both really good objects, but you're only going to get them just after the sun goes down, which is about 8ish at the moment, I think. Right, so another interesting object to look if you've got binoculars or a telescope. Don't think you'll be able to see them with the naked eye, but quite easy to find, very high up at the moment, are two interesting galaxies, the Whirlpool Galaxy and the Pinwheel Galaxy. Now, most of us can find the Plough, it's quite easy to find. So what we're actually looking at here in this picture is the last star in the handle of the Plough and the one before it. And as you can see, the stars are almost like in a triangle and both sides. One's an off, would be a right-angled triangle, one would be equilateral triangle. You can see these two galaxies. And you can see them with binoculars, and well, certainly the Whirlpool Galaxy you could see with binoculars, maybe not so much the Pinwheel because it's not quite as bright. But just something to go and have a look at if you have got a telescope or binoculars. But what I've actually done here to give you a better idea what they look like is I've snuck in a couple of pictures from our astrophotography section. So here is a picture by Steve, which was taken this week, Steve. So there's the Whirlpool Galaxy. Messier 51A or NGC 5194. It's an interacting galaxy, so you can see that it's interacting with with the galaxy below there. So the black holes in both of these galaxies are pulling material away from each other. So it's in the constellation of Canis Venacti. Age about 400 million years, radius of 30,000 light years, apparent mass 160 billion, distance from Earth 23.16 million light years, 100 billion stars. So that's quite an interesting object. The other one is the Pinwheel Galaxy, and this is an excellent picture as well. From another one of our members of the photographic section, Kevin Noble. So there's a bit of information about the pinwheel. Giant spiral disk, 170,000 light years across, nearly twice the diameter of our own galaxy. Estimate contain 1 trillion stars. The galaxy spiral arms are sprinkled with large regions of star-forming nebula. That's the pinky colour you can see in there. That's just revealing hydrogen. Brilliant young stars, hot blue newborn stars. A little bit there about, small central bulge, 3 billion solar masses. Nothing about hard drive. About the black hole in the centre of that, another massive black hole. Most of these spiral galaxies and a lot of the bigger galaxies have supermassive black holes at their centres. So, moving away from galaxies and meteor showers, so we've got the Lyrid's meteor shower coming up shortly, April 23rd. That's quite a nice image I stole off the internet. So they're coming from the constellation of Lyra, and it's quite easy to find because one of the bright stars in Lyra is Vega, although it's starting to set now, as it's really a part of the winter triangle. But from the I think it'll be west, won't it? From the 22nd of April, if you look in that direction, I think it's mainly from the west, you'll see, if you can find Vega, it's quite a bright star. You should be able to see quite a few meteorites. Okay, now I'm going to a few pictures. I thought this was a really good picture. Another one of our astro imagers, Michael, has taken this wonderful picture of the moon. He's brought out the mineral effect of it, but he's actually put some equipment down to let us know what he's used. So the NEQ6 is the mount he's got it on. That's the Skywatcher mount, and he's got 150 millimeter reflector, I would say that is, and a Canon camera. So and he's using EQ mod to drive the mount, and he's for doing his processing. He's using AutoStack Art, which is a German software, and Photoshop. And he's used 60 raw images for that. So really good image. Well done, Michael. It's one of mine, a Sol Nebula I took last week, I think. It's quite interesting. It's another star-forming area. A little bit of information there about mythology, Queen of Ethiopia. More spectacular, a large star-forming region called Sol Nebula, found in the direction and constellation of Cassiope. Cassiope obviously is the W you see in the sky, so it's quite easy to find this particular nebula, but it's not particularly bright. But there's a little bit of history about the mythology attached to it. So again, a star-forming area. The only thing I've put on there, a little bit of information about that it's 6,500 light years away, and 100 light years, about 100 light years in length. So this is a rather good picture Steve's taken of Abel 12, which is a planetary nebula. A planetary nebula is a nebula which is a star similar to our sun, which at the end of its life expands and throws off all its material. So this one's quite difficult because it's right next to a star. So he's done very well to pick that out. I think there's a bit of information about it. It's 6,900 light years away from the Earth. And he's just mentioned their northern outer red hydrogen shell has been ruptured to allow the oxygen to spill out. So as you can see, the oxygen is the bluey green coming out. But that's quite a small object, so well done, Steve, to pick that out. Another one from Michael. This is the Heart Nebula in Cassiope again. The Sol Nebula I showed you earlier on is a companion of this, and it sort of sits just over to the back of where that is now. It just explains the difference between an emission nebula and a reflection nebula. An emission nebula means that the light's actually been generated from the nebula itself, where a reflection nebula is the stars around it and the light is being reflected off from those stars. So, yeah, so this is the Heart Nebula. Just interesting point here, the centre section of the nebula is where the stars are being born at the moment. And I took a picture of that earlier on. So this is the very centre section. Picture I took on a larger scope. And it just says what energises the Heart Nebula, where it's a large emission nebula, like a human heart, but this particular central part, as you can see, the stars being formed in the large clouds of hydrogen. So this is the Rosette Nebula. I took this a while ago. Another star-forming area. These black lines you can see are hydrogen arms are full of star forming. I've actually taken the stars out of this image just to bring the detail out a little bit, because there's so many stars in here they almost wash out everything else. So this is the California Nebula, so cool because it's meant to look a bit like the state of California in America. I'm not sure that it does, but there you go. But interesting nebula. Again, this is quite a bright nebula and it's fairly large. Again, it's starting to wane a bit now because it's really a winter constellation. But again, a little bit of information there about it. It's between 1,000 and 1,500 light years away, and it's 100 light years from end to end. And it's much larger than the Orion Nebula, which everybody sort of is familiar with as being one of the really bright nebulas, but this is much larger. There's another interesting picture by one of our astrophotographers, Michael, again. This is the Cone Nebula. The Cone Nebula is a bit right at the top. It looks like a cone, but the main part of this nebula is called the Christmas Tree Nebula because it does look a little bit like a Christmas tree. But it's in the Orion arm of the Milky Way, so it's a huge, again, star-forming area. And the last image I got to show you, which is one of Steve's, is really good. This is Bode's Nebula, but it's really a galaxy. So, and the Cigar Galaxy, which is the one on to the right of it, M82, in the constellation of Ursa Major. But interesting there, the spiral contains, the Bode's Nebula contains 250 billion stars. M82 is an irregular starburst galaxy, both approximately 12 light years away. 12 million light years, I would say it's probably. I don't think they're 12 light years away. They'd certainly be very visible if they were.
Yeah. Sorry.
Just to see if I was awake, wouldn't you? So great picture, Steve. So really that is my presentation for tonight. I hope if there's any questions, I'll be happy to answer them. But if not, I shall pass over to Alan.
Okay. Am I back with you? Right, I'm back with you now in the room. Thank you very much indeed, Martin. Absolutely brilliant. It gives me great pleasure now to hand you over to Jerry, who's going to introduce tonight's speaker. So over to you, Jerry.
Right, good evening, everyone. So good to see so many of you here. I also need to say thank you to Alan, as he actually arranged tonight's speaker. We had a problem with the person that I had engaged, and I was actually in hospital when he had to sort things out in my absence. So thank you, and also thank you to Andrew Norton for stepping in at short notice. Andrew is the, let's get this right, Professor of Astrophysics Education at the School of Physical Sciences at the Open University. He's held various other positions at the Open University during the last 20 years, plus other positions, including at the OU, the University of Southampton, and he was editor-in-chief of the journal Astronomical Review. During the meal that we had prior to the meeting, we had a lovely chat, which I really enjoyed. And he's actually a fairly busy person giving talks around the country. And we're very pleased that he's here tonight. He's going to speak about the new cosmology, or how the universe works, which I'm sure we all want to know. So I'll transfer the mic back over to him.
Thank you.
And please welcome Andrew Norton.
Thank you. Thank you very much, Jerry, and thanks for inviting me. It's a great pleasure to be here at the Society to give a talk this evening. Yeah, so the new cosmology, or how the universe works, it's kind of the biggest title I could think of, I suppose. Yeah, so we'll see how we get on. I'll start with this image. You've probably seen this one. This is one of the James Webb Space Telescope images. And this image really summarizes everything I'm going to talk about, because here we've just got a random patch of sky, and of course it's full of galaxies. Virtually every splodge of light you can see there is a galaxy, apart from the ones with the sort of diffraction spikes, which are foreground stars. Everything else in there is a galaxy. So that tells us the universe is full of galaxies. But the other thing it shows us really very nicely is these distorted arcs. Now, I don't know if my, I don't know, those of you in the room can see my laser pointer there. Things like this, these arcs, are gravitationally lensed galaxies. So these are background galaxies whose light is traveling towards us through the space which is distorted by the foreground galaxies. And so these sort of arcs are the distorted images of background galaxies caused by the curvature of space due to the gravity of foreground galaxies. And that's really everything I'm going to talk about. I'm going to talk about galaxies, and I'm going to talk about gravity and how gravity controls the universe. The other thing I wanted to say right at the start, I'm calling this the new cosmology, but in fact some of the ideas at the basis of this go back a surprisingly long way. Back to the 1750s, would you believe? You may know Thomas Wright, the English astronomer, in around about 1750, and Immanuel Kant, the German philosopher, in 1755, both of them independently really came up with the idea that our Milky Way is what we would now call a galaxy, a rotating accumulation of stars held together by gravity, and the fact that other nebulae, as they were then called, as we've just seen in some of the fabulous photographs, are other galaxies, island universes, as perhaps the phrase was at the time. And as I say, that goes back over 250 years. So some of this new cosmology is perhaps not quite so new as we might imagine. Anyway, here's what I plan to talk about. I'll talk about how we measure the distance to galaxies, how we measure the speed at which they appear to be moving. Appear to be moving is perhaps a phrase there that I'll come back to. And I'll talk about how that leads us to this idea of expanding space, and indirectly then to the age of the universe. I'll then talk a little bit about what we call black body radiation, which leads us to the cosmic microwave background and the temperature of the universe, both of which point to the fact that the universe began with an event we now call the Hot Big Bang, about 13.6 billion years ago. And having quickly sailed through that history of the universe, I'll then talk a little bit about the future of the universe and how we understand that with our picture that we now have of dark matter and dark energy. And I'll end up saying a little bit about the fate of the universe. Now, I just thought when we set this up, a couple of my videos later on have some sound. It'll all just go through the cables okay, will it? Fine, right. Everybody will hear that when we get to it. Good. So just a picture to start with then of some telescopes. to remind us that, you know, this is how we obtain our information about the universe. And we've seen some fabulous photographs already this evening with telescopes that, you know, many of you can get your hands on. But these are the ones we wish we could all get our hands on. These are, well, the imaginatively named Very Large Telescope in Chile. It's actually 4 telescopes, each of which has a mirror about 8 meters or so in diameter. And of course, this fantastic site is up in the Andes, so it's actually above the clouds. In the distance there, you can see the clouds below, looking rather like the sea, but that's just the clouds from above, and the mountains poking out above the top of the clouds, where you're above most of the Earth's atmosphere, certainly above a lot of the water vapor, which causes the absorption in the atmosphere. So this is, of course, one of the best sites possible for astronomy. So, the expanding universe then. It's based on the measurement of 2 quantities, really. The distance at which galaxies are away from us and the apparent speed with which they appear to be moving. And in order to interpret those measurements, as I'll show you, we make one assumption, and it is just one assumption, which turns out to be a very powerful assumption. We assume that the laws of physics are the same at all places and all times in the universe. So the laws of physics that we measure here today on Earth are the same as operate elsewhere in the universe at any other time in its past or future. And if we make that one assumption, we can actually deduce an awful lot about how the universe is behaving. So what can actually be measured then? Well, in simplest terms, it's just light. Apart from the odd meteorite that lands on Earth or a bit of moon rock brought back by the Apollo astronauts, the only thing we can measure from out there in space is light. And I'd use that in its most general term, so any form of electromagnetic radiation, whether that's radio waves or X-rays or whatever, but light in general then. And mostly I'll be talking about visible optical light tonight as well. 2 sorts of measurements we can make, broadly speaking. Photometry, the amount of light, the brightness of something, and as I'll show you, that can help us infer the distance to objects. And spectroscopy, spreading the light out into its constituent wavelengths or frequencies. That allows us to measure what we call the redshift of a spectrum, and that, as you may know, lets us work out the speed with which something appears to be moving. So they're the sorts of measurements we have. And of course, when we look at out there in space, we're looking at galaxies. We've seen some images already this evening. This is the Andromeda galaxy, the nearest large galaxy to our own Milky Way. And of course, this is something like what our Milky Way galaxy would look like if we could fly outside it and look back at where we are in one of the spiral arms of our galaxy. But here's the Andromeda galaxy then, the nearest large galaxy to us. And let's start thinking about distances. We've already, in the images earlier, heard about the distances to some of these galaxies expressed in light years. An alternative unit that you probably have come across is the parsec or the kiloparsec, thousands of parsecs. And using this sort of measurement, here's the sort of distances we're talking about. So our own Milky Way galaxy is about 40 kiloparsecs, 40,000 parsecs across. The nearest large galaxy, the Andromeda galaxy, is about 800 kiloparsecs away. And the Milky Way, the Andromeda galaxy, and a couple of dozen others form what we call the local group of galaxies. And the distance from the local group of galaxies to the nearest significant cluster of galaxies, the Coma cluster, is about 100 megaparsecs, 100 million parsecs. Now, it's all very well to sort of bandy these numbers about, and we can write the numbers down and we can sort of imagine them, but can we really grasp how big these distances are? And I certainly find it very difficult. But here's one way I can try and imagine how far a kiloparsec is. Okay. So imagine traveling at 1,000 kilometers per second. That's really fast, but you can just about imagine that, perhaps 1,000 kilometers a second. Okay, 3 times the speed of, no, however many 100 times the speed of sound. Anyway, imagine traveling at 1,000 kilometers per second. That's Land's End to John O'Groats in a second. every second, Land's End to John O'Groats. Imagine travelling at that speed for 1 million years. Then you would travel 1 kiloparsec. Okay, 1,000 kilometres a second for 1 million years, that's 1 kiloparsec. And Andromeda is 800 kiloparsecs away, and that's just the nearest big galaxy. So I don't know, maybe that doesn't help, but it's a way to try and get the hang of how big these distances are. And when we think about measuring the distances to things, we often talk about this so-called cosmic distance ladder. It's really giving us the idea that different methods are used as we move further and further out into space. So in our sort of local patch of space within the solar system, we can use radar ranging. We can bounce a radar signal off the moon, measure the time delay it takes to come back, and use that to work out the distance away. And we can do that from other spacecraft in the solar system and so on. Within our own galaxy, we can use a geometric technique called stellar parallax, particularly now with the European Space Agency Gaia satellite, which is measuring the positions of 1 billion stars in the galaxy. And it does it by this geometrical technique of parallax. Essentially, you're probably familiar, you can hold up a finger in front of your face, close one eye and look at it with the other, then switch eyes, and your finger appears to jump backwards and forwards against side to side against distant objects. That's essentially what parallax is. Instead of your two eyes, it's the Earth that in, say, summer and winter at opposite ends of the orbit. And as we look at nearby stars from one end of the Earth's orbit to the other, they appear to shift with respect to background stars. Gaia can measure those parallaxes to 10 milliarc seconds. Okay, an arc second being 1/3600th of a degree, and Gaia can measure those parallax changes to an accuracy of about 10 milliarc seconds, which turns out it can then measure distances to about 10 kiloparsecs away, which is about as far as the centre of our galaxy. So just by geometry, we can measure the distance to stars within at least half of our galaxy. Going further still, we can make use of variable stars where we measure their brightness, and certain variable stars like RR Lyrae variables or Cepheid variables have particularly recognizable variations in brightness, and we can relate that variation that we measure, the period of variation, to their luminosity. So if we calculate their luminosity, we measure their brightness, we can work out how far away they are. Further away they are, the fainter they appear for the same luminosity. And that's useful to maybe within 40 megaparsecs, so several nearby galaxies, many nearby galaxies. That enables us to measure their distances. And going further still, we can use supernovae to work out distances again. We determine the luminosity, we measure the brightness, we work out the distance. And then ultimately, the Hubble law, sometimes now called the Hubble-Lemaitre law, which I'll come to a little bit later. But essentially, using brightness measurements to work out distances, and that's just sort of summarized here really, brightness being proportional to the luminosity divided by the distance squared. So the further away something is for the same luminosity, the fainter it appears to be. We call these sorts of variable stars and supernovae, we call them standard candles. Okay, they're not a candle, of course, but they have a standard luminosity or a standardizable luminosity, and it's that enables us to work out the distance from the brightness. The other side of this then is looking at spectra, as I mentioned. So at the top there's a spectrum displayed as a rainbow of colours. The middle graph is that same spectrum converted into a graph of intensity against wavelengths. So that's a spectrum of a typical star. And the dips labelled A, B, C, D, E are some spectral lines in that star, some absorption lines, where elements in the outer atmosphere of the star cause an absorption at certain wavelengths. And those absorption lines occur at very specific wavelengths that we can measure in laboratories here on Earth. If we then look at a spectrum of, say, a distant galaxy, it will look like typically the spectrum of stars, because of course a galaxy is made of stars, at least the luminous parts that we can see. But when we look at the spectra of other galaxies, we invariably see that the same pattern of spectral lines are shifted towards longer wavelengths, towards the red part of the spectrum. So this is obviously what we call a redshift. And you know, it's easy to understand what this is in terms of an analogy, really, the Doppler shift that I'm sure you're all familiar with. You know, a source of sound moving towards us or away from us. If we're there, the observer labeled A with the ambulance approaching them, the sound waves from the ambulance siren get bunched up in front of the ambulance as it catches up the crests of the sound waves. So the person at A perceives a shorter wavelength, a higher pitch of sound, and the opposite for the person on the other side, B, as the siren moves away, the wavelengths get stretched out, and so that person perceives a longer wavelength, a lower pitch of sound. So that's the Doppler shift with sound. Exactly the same thing really occurs with light. So an initial interpretation then of that redshift would be that these galaxies are moving away from us. The wavelength of the light is stretched out to longer wavelengths, lower frequencies towards the red part of the spectrum. So we could interpret that that redshift as a speed. We define the redshift as simply the change in wavelength divided by the original wavelength, and then multiply that by the speed of light to get the apparent speed. So that graph, the spectrum I showed you a moment ago, one of those particular lines was shifted from 590 nanometers to 618. That's a shift of 28 nanometers, a redshift of 0.047. Multiply that by the speed of light, 300,000 kilometers per second, and you get an apparent speed of 14,000 kilometers per second. As you probably know, one of the first people, if not the first person to spot this, was Edwin Hubble, seen there smoking his famous pipe. He sadly did die of lung cancer, but there we are. You always see him smoking a pipe in these photographs. And he, in the 1920s, was the first person to observe that if you look at galaxies beyond the local group, all galaxies exhibit redshifts, none exhibit blue shifts. Within the local group, there's a mix. Some are moving towards us, some are moving away from us. In fact, the Milky Way and the Andromeda Galaxy are moving towards each other. So the Andromeda Galaxy as a whole shows a blue shift. But beyond the local group of galaxies, all other galaxies exhibit redshifts. So all other galaxies appear to be moving away from us. And furthermore, what he noticed, most crucially, the more distant a galaxy is, the faster it appears to recede from us. And that's illustrated in the graph there. Each dot is a measurement of an individual galaxy, shown a little schematically here, but at the vertical axis is the recession speed in units of 10,000 kilometers per second. On the horizontal axis is the distance in units of megaparsec. And as you see, the further away a galaxy is, the faster it appears to be moving. And the gradient of that graph, which we now call the Hubble constant, in this particular example, is about 72 kilometers per second per megaparsec. In other words, for every megaparsec further away you go into the universe, galaxies appear to be moving 72 kilometers per second faster. In fact, the best current value for this, as we measure it, is about 67.7 plus or minus a half kilometer per second per megaparsec. And that's the current value, as we measure it, of the Hubble constant. Labeled as H subscript naught, because that is the value that we measure it today, now. It was most likely different in the past and will be different again in the future, but the value that we measure at the present time, H naught, about 67.7 kilometers per second per megaparsec. This is just an example of trying to understand that. It doesn't mean that we're somehow in the centre and everything is rushing away from us. It's interpreted to mean that space itself is expanding, and you'd measure this same redshift effect wherever you happen to be in this expanding space. And here's one way of sort of visualizing that. This is a one-dimensional universe that looks like a strip of elastic with buttons sewn onto it. The buttons are the galaxies, and the elastic expands, space expands, and so all the galaxies recede from each other. And in this particular example, B recedes from A at 4 megaparsecs per billion years, which is equivalent to about 4,000 kilometers per second. And wherever you measure that at the present time throughout space, you would measure the same value. So in this one-dimensional example, there's some examples there, measurement of B from A, or C from A, or B, D from B, whatever. You measure the same value of the Hubble constant, because the more space there is between the two galaxies, the faster the expansion, because there's more space between us and them. Therefore, the further away they are, the faster they appear to move. However, the Hubble constant is not the same, as I already hinted, throughout time. If we look at this example here, 9, 10, 11 billion years, say, where let's pretend today is at 10 billion years, measurements of B from A, the Hubble constant gets smaller as we go forward in time. In this particular example, if the universe expands at a constant rate, if this one-dimensional universe expands at a constant rate, the Hubble constant, the Hubble parameter, perhaps more better described, will decrease with time. As I'll come back to later, we're now beginning to see in the last 20 years or so evidence that the rate of expansion of the universe has changed at different times in the history of the universe. I'll come back to that. Anyway, that's enough of those numbers for the time being. Let's look at a couple of nice pictures. This, I think, is this M51 that we saw earlier? I think it might be, yes. Just really to remind us how beautiful the galaxies are. You know, in galaxies like this, as I mentioned earlier, we can see some of those variable stars, like the RR Lyrae stars, like the Cepheid variable stars, if we're lucky, supernovae that go off randomly. So we can use those standard candles to measure the distances to these galaxies. And there's another one, nice barred spiral galaxy. I'm afraid I've forgotten which one that is, but somebody will know. There we are. Anyway, let's think about a few difficult ideas then, because you know, we hear these things about expanding space, and we think, well, okay, what's the universe expanding into? Difficult question. Well, it's not a good answer, but this is the best I can do. It's not an expansion into space, it's an expansion of space itself. Matter is more or less fixed. We here on Earth, the solar system, our own galaxy, our local group of galaxies are not expanding. We're held together by gravitational forces and sort of chemical forces, really electrical forces. It's only on the largest scales that this expansion of space wins. How big is the universe? Well, that is a really difficult one. Probably infinite, probably goes on forever, and probably always has been infinite. You know, we think about the Big Bang as being the origin of the universe, but the best way of thinking about it is that the universe was even infinite at the instant of the Big Bang. It's just things have got further apart since. It's difficult to get one's head around it. So I try and be careful and say space is expanding, not the universe is expanding. The universe has always been infinite, probably, but the space between things is getting bigger.
I don't think a physicist should say a statement that it's probably infinite. I think.
Well, we don't know.
Yeah. I mean, one can just say there's nothing and it's expanding into an infinite amount of nothing.
No, I don't think that's right, though. I don't think that's right, because space is a property of the universe. The universe doesn't sit in space. Space is of the universe.
That's debatable. because space is a debatable thing. I mean, because you can take a spin.
we hold the questions to the end?
So, okay, yeah.
Okay. Yeah.
It's very controversial.
Well, some things are, definitely, yeah. This is an analogy that is often used. I'm not sure I'm a big fan of it. The balloon as being a two-dimensional surface. We say, where is the centre of expansion in our three-dimensional universe? Well, I don't think there is a centre because it's expanding everywhere at the same time. In a two-dimensional universe, the surface of a balloon, as you blow the balloon up, the surface of the balloon gets bigger, the buttons, the galaxies get further apart, but in that example, the centre of the expansion is not within the universe because the universe is only the two-dimensional surface. I'm not sure that that helps picture our own universe. It's a difficult one to imagine. And this goes back to the idea of an infinite universe as well. If the universe is infinite, then there is no edge. There's no outside, since space only exists within the universe. The universe isn't located in space. Space is a property of the universe. That's not to say you would necessarily go on forever. You may head off in that direction and end up coming back behind yourself if you go far enough, if the universe is closed in on itself. But we don't know the answer to that one. But I think there can't be an edge. But these are difficult questions. So, let's think about the age of the universe then. We've measured, I've misquoted myself already, I've said the universe is expanding. I should have said space is expanding. All galaxies were closer together in the past. If we assume space has been expanding at a constant speed, which it hasn't, but if we assume for now that it had, then the galaxies would be at zero separation at a certain time in the past. And if galaxies that are currently 500 megaparsecs apart are currently separating by 36,000 kilometers per second, then at a time given by that distance divided by speed, they would be a zero distance apart. So if the universe has been expanding at a constant rate, the age of the universe, it's actually 1 over the Hubble constant, is about 14 billion years, assuming a constant speed of expansion, which, as I'll show you, is not correct. But that gives us a ballpark, 14 billion years for the age of the universe. The other aspect then, apart from the expansion, is this idea of a cooling universe. What do we mean by the temperature of the universe? We think space is empty. Well, it is, apart from the photons it contains. The universe contains, away from all the stars and galaxies, about 400 million photons per cubic meter. And those photons have a particular distribution of wavelength or frequency or energy that we call a black body spectrum. Now, black body spectra are these black lines here. A gas of different temperatures will have a spectrum corresponding to one of those shapes that will peak in different parts of the electromagnetic spectrum. The hotter they are, the shorter the wavelength. So to ultraviolet, X-ray, gamma ray, they will peak. This all sort of became relevant way back in the 1960s. These two guys, Arno Penzias and Robert Wilson, working at Bell Telephone Labs in New Jersey, they were developing this new technology to track satellites using microwaves. And the antenna there behind them, the horn antenna, was what they were tracking some early satellites with. And to their dismay, wherever they pointed this horn antenna on the sky, they detected a background glow, which they didn't know what it was. They thought it was just noise, interference. They first of all thought it was due to pigeon droppings in the antenna. They cleared that out. The pigeons made more droppings, so they got rid of the pigeons. The pigeons came back, then they shot the pigeons didn't come back, and they still had this background glow from the entire sky. Luckily, they then spoke to some colleagues down the road at Princeton University who said, well, this is just what we predicted. There should be a background glow from the Big Bang, and that's what you've detected by accident. And Penzias and Wilson won the Nobel Prize for their accidental discovery. What this was then, the microwaves that they'd discovered, were a black body spectrum in the microwave part of the wavelength range corresponding to a black body with a temperature of just 2.73 degrees above absolute zero, 100 times colder than the freezing point of water, about 3 degrees above absolute zero. That spectrum is what was measured by the Cosmic Background Explorer satellite in 1990. The error bars on those data points are too small to see. It's the most perfect black body spectrum that we have anywhere in nature. It's been, sorry, before I come on to that, black body spectra require a thermal equilibrium in order to produce them, and that generally means you need high temperatures. So how can you get a black body spectrum at just 3 degrees above absolute zero? The key is that when the radiation was in thermal equilibrium with matter, it was 1,000 times hotter. About 300,000 years after the Big Bang, the temperature of the universe was about 3,000 Kelvin. The expansion of space has cooled the radiation, stretched out its wavelength ever since. So at a redshift of 1,000, when this radiation was emitted, it was infrared radiation corresponding to a temperature of 3,000 Kelvin. Now, when we measure the radiation today, it's 1,000 times cooler at just 3 degrees above absolute zero. But it's not constant across space. Here's a map made with the Wilkinson Microwave Anisotropy Probe in 2003, and this is a map of the temperature distribution of the cosmic microwave background across the entire sky. These fluctuations are of order a 10,000th of a degree either side of that mean value of 2.73. Somewhat unusually, perhaps the red spots are slightly hotter, the blue spots are slightly cooler. And what these are interpreted to represent are the temperature distribution of the universe at the time when that radiation last interacted with matter 300,000 years after the Big Bang. And so what they're telling us are the localized places where there was slightly more matter or slightly less matter, which have since coalesced to form the clusters of galaxies that we now see. And at the time when these were discovered, they were claimed to be ripples in the fabric of space-time, which is quite a nice phrase, I suppose. So there's then three main pieces of evidence for the hot Big Bang, two of which I've talked about. The expansion of space that tells us the universe was denser in the past, and the cosmic microwave background that tells us the universe was hotter in the past. The third piece of evidence, which I haven't touched on, is the relative abundance of the elements, that the early universe was about 3/4 hydrogen, 1/4 helium. That's a whole other talk. Let me then see if we can have a little cartoon. Is this starting? No, start it with that. Here we go. This is one of our 60-second adventures in astronomy that you may have seen on the web.
60-second adventures in astronomy. Number 1, the Big Bang. Just how big was the Big Bang? The idea that the universe is expanding as the result of a single explosion wasn't always universally popular. In fact, the term Big Bang was coined in 1949 by astronomer Fred Hoyle as a way of sarcastically dismissing it. But thanks to Edwin Hubble, we now know our observable universe is expanding. And extrapolating backwards, we can tell that 13.7 billion years ago, it was all compacted into one superdense ball. And this singularity expanded and cooled to become everything in the universe that we see around us. So though the Big Bang involved everything in existence, its beginnings were really quite small. And after measuring the background radiation in the universe, astronomers have worked out that the Big Bang was only around 120 decibels, about the volume of an average rock concert. So while the Big Bang still has a lot to teach us about the universe, we do know, at least to start with, it wasn't particularly big. And it wasn't much of a bang either.
Anyway, a bit of fun, may not be entirely true. There we are. Right, I've got another one of two of those to show you later. So that's the history of the universe. Let's now think about the future of the universe. What's the universe going to do in the future? We can think about that in terms of an analogy. If we imagine launching a rocket from the surface of the Earth, it's a balance between kinetic energy and gravitational energy. If the rocket has a large kinetic energy, it will escape into space. If it has a small kinetic energy, it will eventually fall back again. As with the rocket, so it is with the universe. We can imagine two scenarios, what we call an open universe, kinetic energy wins, the universe will expand forever. A closed universe, gravitational energy will win, and the universe will collapse again, in on itself. Those possibilities, open and closed universe, relate to the density of the universe and what we call the curvature of space-time. We can imagine them in two dimensions in this way. The familiar geometry that we have in everyday situations, a flat geometry, the internal angles of a triangle add up to 180 degrees. That would be a curvature of 0, k equals 0. If we have a high density universe, that's described by a positive curvature, such as the one on the left, where the internal angles of a triangle add up to more than 180 degrees. If we have a low density universe that would expand forever, that corresponds to a negative curvature of space, k equals -1. So, the future of the universe depends on the geometry of the universe, which in turn depends on the density of the universe. In a high density universe, gravity wins, the universe is closed, it will eventually collapse. In a low density universe, the expansion wins, the universe is open, and it will expand forever. Obviously, if you've got those two extremes, you've got a dividing line between the two, a critical density or flat universe, which I think it was John Barrow, British cosmologist, called it the British Compromise universe, exactly balanced between the two. That critical density universe would expand forever, but always decelerate, reaching a 0 expansion rate at an infinite time in the future. And we can tell what the curvature of the universe is looking at those maps of the cosmic microwave background. Here's some more detailed measurements on a small patch of sky made with an experiment called Boomerang. And at the bottom are 3 simulations corresponding to a positive curvature, a flat curvature, and a negative curvature. And you can see by eye, but you can work this out computationally as well, the distribution of fluctuations that we see in the cosmic microwave background correspond exactly to a flat universe, curvature of 0. So, measurements of the cosmic microwave background indicate that the universe is flat. It has this exactly critical density. Space-time is simple, if you like. The parallel lines remain parallel, the internal angles of a triangle always add up to 180 degrees. The density of the universe is equal to the critical density. We describe that by saying omega, the density, equals 1. And that critical density corresponds to about 5 protons per cubic meter. Doesn't sound a lot. The trouble is, when we measure the density of the universe by adding up all the stuff we can see, all the galaxies and stars that shine by light, emit light, all the luminous matter, when we add up all that, it only gives us 0.005 of the critical density, 0.5%. Something is going wrong. The first clues to what it was were really down to these two people, Fritz Zwicky on the one hand and Vera Rubin on the other. In the 1930s, Fritz Zwicky had looked at the movement of galaxies in clusters and determined there must be some other mass there that he couldn't see that was controlling that movement. And then rather more recently, in the 1970s, Vera Rubin measured what are called rotation curves of galaxies, looking at how the stars in the outer regions of galaxies move, the speeds with which they rotate around the center. And the speeds with which they're measured to move depart from how you would calculate they should move based on the gravity due to the mass that you can see. So both of these were indicating that there's some hidden mass, hidden matter somewhere in the universe that we can't see, but which is controlling how things move. Modern terms for these are machos, massive compact halo objects in the halo of our galaxy and other galaxies, and the WIM, the warm, hot intergalactic medium, gas between the galaxies. Let's have another cartoon. There we go. Okay, a little cartoon about dark matter.
60-second adventures in astronomy. Number 8, dark matter. What's the matter with dark matter? Fritz Zwicky was a Swiss astronomer who could probably get you 81 points on a triple word score in Scrabble. In the 1930s, he noticed that galaxies within clusters were zooming around far quicker than their mass would logically dictate. So he figured that there must be some extra mass in there, some sort of dark, invisible matter slurping around the universe. He imaginatively called this dark matter. But the problem is trying to prove it, because unlike other dark things, you can see right through this stuff, and this gave Zwicky another idea. According to Einstein's theory of general relativity, the more mass something has, the more it magnifies and distorts objects that you can see through it. So by studying the distortion of distant galaxies, we can calculate that there must be some extra mass between us and them. But because we can't see it, touch it, or weigh it, it's not surprising that we can't figure out exactly what it is. And that's what the matter with dark matter is. It makes up most of the mass in the universe, but when it comes to knowing the details, we're still in the dark.
Right. So that's where we were 30 years ago, perhaps. Then we had a clue from supernovae. Supernova remnants, like the Crab Nebula, the remains of an exploding star. Broadly speaking, there are two types of supernovae. When massive stars, more than, say, 20 times the mass of the sun, reach the end of their lives and explode, they throw off the cloud of the outer material and collapse to form a neutron star or a black hole. But there's another type of supernovae that we think happen in interacting binary stars, where you start off with a low mass, say a red dwarf star on the right there, distorted into that pear shape by the gravity of its companion, which is a white dwarf star sitting there in the center of this flat accretion disk. So the white dwarf is pulling material off its companion. White dwarfs, we know, can only exist up to a mass of 1.44 times the mass of the sun, called the Chandrasekhar limit. Above that mass, they collapse. They can't hold up due to electron degeneracy pressure, and they collapse. So if you have a white dwarf accreting material from a companion, which eventually goes over 1.44 solar masses, it will explode as a supernova, a so-called supernova type 1a. And because they all explode at 1.44 solar masses, they should all have the same luminosity. So we can use them as a standard candle. We measure the brightness, we calculate the luminosity, we work out how far away they are. And back in 1998, this is one of the measurements, Saul Perlmutter et al. Measured some supernovae in distant galaxies in the supernova Cosmology project. So the red dots there with error bars are brightnesses of distant supernovae as a function of redshift. If the universe has a critical density, and all of that density is caused by matter, then the supernovae should lie along the middle one of those three black lines. But you can probably see those more distant supernovae at redshifts 0.5 and 1 sit above that middle black line. Those distant supernovae are fainter than they should be. The interpretation then is that the expansion of the universe is currently speeding up, accelerating, not slowing down or decelerating as we previously thought. So the light from those supernovae has travelled a greater distance than we previously thought. That's why they appear fainter. Now, turns out Einstein had thought of this nearly 100 years ago, although didn't realise he'd thought of it. It suggests, this fainter type 1 supernovae suggests that there's some kind of negative gravity. We now use the phrase dark energy, pushing the universe apart faster and faster. And Einstein had already thought of this 100 years ago when he came up with his equations of general relativity. His equations predicted that the universe must either expand or contract, and at the time, this is pre-Hubble, we didn't have any reason to suspect the universe was anything other than static. So he introduced into his equations something he called the cosmological constant. After Hubble's discoveries, Einstein said, "Oh, what a blunder I made. I was wrong." But it turns out you can describe this dark energy using exactly what Einstein had put into his equations as a cosmological constant. More evidence that this was right came in, again, the late 1990s. This is a supernova at redshift 1.7. So there's a little box at the top, zoom in, and then subtracting the starlight. There's the supernova. That one at redshift 1.7 is brighter than it should be. So here's the idea. So this is a graph of difference in brightness of supernovae against redshift. Look, just look at the bottom graph where the points have been sort of binned together. So the black points with the error bars are the measurements of supernovae. If the universe had been constantly decelerating, they would lie along that line. If the universe had been constantly accelerating, they would lie along that line. But in fact, they lie along this curve. So the universe is currently accelerating, but in the past, it was decelerating. So there we go. As we look further back in time, the current acceleration turns into a deceleration. The supernovae in that redshift range 0.3 to 0.8 are fainter than expected. They're in the nearby recent accelerating universe. The supernova that was observed at redshift 1.7 is brighter than expected. It's in the more distant early decelerating universe. Okay, one final cartoon. Let's see if we can do that. Ooh, there we go.
"60-second adventures in astronomy. Number 9, dark energy. Why is the universe expanding? Albert Einstein was absolutely certain the universe was stable, but he couldn't work out why his snazzy new relativity equations suggested that it was contracting. So Einstein figured space must have an inbuilt tendency to fling itself apart, which would balance out the pull from gravity. This flingy outness got called the cosmological constant and meant the universe could be kept static, which was great, until it was proved by Edwin Hubble that the universe is in fact expanding, and that cosmological constant became what Einstein described as the biggest blunder of my career. Then, in 1998, scientists discovered that the universe was not only expanding, but that expansion was actually getting faster. So either space does have a tendency to fling itself apart, or there must be some other hidden weird stuff in the universe causing it, referred to as dark energy. Astronomers are looking for it right now by measuring tiny kinks in space. And in its simplest form, this dark energy is pretty much a cosmological constant. So Einstein was right all along, apart from the time he said he'd blundered. The big thicko.
I love tiny kinks in space. I think that's one for the older ones amongst us. I think I've just broken the microphone. Oh, I'll just clip it on there. That's all right. It's still there, I think. Okay. Oh, done that. So, here we go then. What have we got to? If the universe is flat, as we measure it to be, then this omega density is equal to 1. If it's all matter, we say omega m equals 1. But the supernova results imply that this is omega lambda, dark energy as well. Energy equals matter, we know, equals mc squared, so you can add up the matter and the energy contributions. So we know that omega matter plus omega dark energy equals 1. From the supernova measurements, from the cosmic microwave background, we work out that omega matter is 0.31, 31%, and omega lambda, dark energy, 0.69, 69%. So here then is what the universe is made of. The universe is made of about 0.5% stuff we can see. Stars, galaxies, dust, us. That's 0.5%. There is other dark matter made of atoms that we can't see. It's baryonic dark matter. It's made of the familiar atoms, protons, neutrons, and so on. That's what I mentioned earlier. Machos, the massive compact halo objects, maybe dark, dead stars in the halo of galaxies, or the WIM, the warm, hot intergalactic medium, coolish gas between the clusters of galaxies. But the rest of the matter, the other 26% of this omega, is non-baryonic dark matter. It's not made of atoms, neutrons, protons, electrons, and so on. We've got no idea what it is. We call it WIMPs, weakly interacting massive particles. That just describes what they are. They don't interact, they're massive, but what are they? 26% of the universe. And the rest of the universe, making up this critical density, 69% is dark energy, the cosmological constant. And we have equally no idea what that is either. But that adds up to 100%, the critical density. All right, last slide or two. What about the future, the fate of the universe then? The fate of the universe depends on the type of dark energy. And critically, it depends on this equation of state parameter W. It's the ratio of its pressure to its energy density. We know that W must be less than -1/3 to cause acceleration, and we know that dark energy gives rise to an acceleration. If W is between -1 and -1/3, the dark energy will dissipate with time, leading to what we call the heat death of the universe. Everything will just fade away, cool down, and go out, and we'll have a dark, cold, dead universe. But here's the exciting one. If W is less than -1, then dark energy will increase with time. Regular matter, if you expand it, it gets less dense. If the equation of state parameter W of dark energy is less than -1, as the universe expands, you get more dark energy. And more dark energy will cause the universe to accelerate its expansion faster and faster. So this leads to what we call the Big Rip. So the galaxies will move further and further apart, then the stars will rip apart, eventually even the atoms will rip apart as space expands faster and faster. Now, what is W? You're anxious to know, I'm sure. We can measure it just about, and it's reckoned to be minus 1.03 plus or minus 0.03. My guess, of course, is that W is actually -1. We're right on the critical boundary. Just as we have a critical density of matter in the universe, matter and energy in the universe, I think it's most likely that we have this critical equation of state parameter for dark energy. So we will get a big rip, but only at an infinite time in the future. So we don't have to worry about it. So there we are then. This is the new cosmology as we now understand it, as we currently understand it. We live in an expanding, cooling, infinite, flat universe, curvature k equals 0. The Big Bang, the hot Big Bang, occurred about 13.8 billion years ago, as determined from the current value of the Hubble constant, Hubble parameter 67.7 kilometers per second per megaparsec. The expansion of the universe, the expansion of space, was initially decelerating, but now, thanks to dark energy, is accelerating. The critical density of the universe is made up of matter and dark energy. 31% of it is matter, mostly dark matter. 69% of it is dark energy. We don't know what dark energy is. We don't know what the baryonic dark matter is, machos and the WIM. We don't know at all what the non-baryonic dark matter, the WIMPs, are. And the ultimate fate of the universe, a heat death or a big rip, we're probably on the critical dividing line between the two, so a big rip at an infinite time in the future. And there we are, plenty still to find out. Much of what I've said may be entirely false, but it's our best understanding as we currently have it. So I'd better stop there. Thank you. Oh, you said, okay.
Thank you very, very much for that, Greg. I mean, it's one heck of a subject to go through. And to finish up with the last line, what's going to happen, we don't know, after doing all this study. I do need to ask first off, though, we're on this critical line between -1 plus or minus. Do you think that that's too much of a coincidence, or is it just the way that the universe is structured that puts us in that position?
I think the latter. I think it must be, mustn't it? It can't be a coincidence, but it may be that if it were not that, we would not be here to observe it as being that.
Okay, fair enough. Right, do we have any questions within
I
the...
can extend to the next part, which is about the coincidence. Because why would there only be one Big Bang for the universe? So the multiverse, do you want to say anything?
Yeah, absolutely. I've got another talk about that, actually. I don't know if you've ever come across the ekpyrotic universe theory, born out of fire. So that ties up with M theory and 26 dimensions of string theory. The idea there is, and say it's a whole other talk, but essentially the universe has 26 dimensions. Most of them are curled up very small, but there's, apart from the regular 3 dimensions of space, 1 dimension of time, there's a 5th spatial dimension. Our universe exists on this membrane, 4-dimensional membrane, and there's, if you like, a parallel membrane separated across this 5th dimension. And so the dark matter is the matter on the other brane leaking through into our universe, and the dark energy is the tension between the 2 branes. So the Big Bang was really a big clap, and the universe expands apart until you get a heat death, and then they come together again, you get another big clap, and so you get an infinite series of big claps, the latest of which is what we call our Big Bang. So that's one way of thinking of...
There's a string theory that says there's multiple
Could you wait for the mic, please?
Sorry, yes.
Because people on Zoom can't hear you.
So the view, I think Ethan Siegel, you know, there's a I haven't looked really at the detail of the maths, but the argument is if the current theories are correct, then there must be multiverses.
Yeah.
So, I mean, it's controversial in the sense it's only come up over maybe the last 20 years, but because the arguments people go against it, there's certain people that say that, well, it's you can't measure it, but you know, there are other Big Bangs. But the question is we do seem to be tuned.
I think it is. The universe is very highly tuned. So, there are lots of coincidences that, were they not as they are, we would not be here.
So a random laws of physics of an immense number of multiverses would just solve. It just says it's a random process.
Yeah.
And so I always ask the question. It's not why is there other universe. The question is why would there only be one?
Yeah.
Because
I agree.
Physics never has a unique thing, and it's like really naive to think this Big Bang.
Yeah.
And it's only now that it seems to be.
Yeah, and if you think, you know, the Earth was displaced from the centre, then the solar system, then the galaxy, and now the universe is probably...
It just seems so obvious after the event that...
One universe is enough for a talk like this, but yeah, exactly. It's the anthropic principle. John Barrow and Frank Tipler read their book on that. It's it comes to that. Yeah.
When I first learned about dark energy and the expansion of the universe accelerating, I mean, that was quite a staggering thing. And I started asking, do we actually need dark energy, or do we just need a better understanding of gravity? And of course we don't have an answer to that.
No.
The other question is about the quantum vacuum.
Hold on.
Hold on. Why the quantum vacuum?
For the microphone.
People
online can't hear.
So the quantum vacuum is effectively an energy term, and the question is, it's 120 orders of magnitude from the
observed
what would you expect?
value.
Anything to say about? Because I don't get to talk to people who might.
No, I don't know, and I don't. I think if anyone claims they do know, they're probably lying. No, we don't know why and what dark energy is, or why it has the value it does, and you know, why should we? Another coincidence, you know, 31% matter, 69% dark energy. That's roughly, you know, 50-50 for an astronomer. Why should we happen to be here at this time when they're exactly balanced? Dark energy could be 1 million times bigger than the dark matter, but they're within a factor of 2 of each other.
Again,
Yeah. Any other questions?
We have a question on Zoom.
Oh, question on Zoom. Okay.
What about modified Newtonian dynamics? Can that explain everything that is currently theoretically explained by dark matter?
Some people claim modified Newtonian dynamics, MOND, can explain dark matter, possibly, but it's, in a way, it's just replacing one unknown with another unknown. We know that Newtonian gravity is only an approximation. When you get to large masses, large speeds, you need, Einstein's gravity, general relativity. Maybe that is an incomplete theory. We don't know. Yeah, we just don't know. Dark matter. We know there must be something making stars in the outer regions of galaxies and galaxies in clusters move at faster speeds than you would predict based on the amount of matter we can see and our current understanding of how gravity works. Whether you say gravity works differently or there's some extra matter is, is exchanging one unknown for another, I think.
Yes.
Hello. That was a great lecture, by the way. I'm afraid I'm going to ask you about what you least know about. And that is the dark energy.
Yeah.
Is it perceived that that was there right at the beginning, or did that condense out like the other forces did of nature?
Yeah, very good question. Yeah, I think it was there at the beginning, but the contribution to the overall energy density of the universe was much smaller at the beginning. At the beginning, the biggest contribution to the energy density of the universe was radiation, electromagnetic radiation, pressure and energy. Over time, the contribution of matter has become dominant, and then within the last 6-7 billion years, the contribution of dark energy has overtaken that of matter, and that's when the deceleration turned into an acceleration, when the dark energy became dominant about half the age of the universe ago. As I mentioned, the thing with dark energy is, as space expands, the matter density gets more diluted, so the density of matter goes down. But as space expands, you've got more space, so you've got more dark energy. So as space expands, the contribution of dark energy increases, and in the Big Rip carries on increasing. So yeah, there would have been dark energy back soon after the Big Bang, but the relative contribution of it was much, much smaller, and it's only become dominant in the last half of the age of the universe.
Yes.
I'm really interested in the lecture, by the way, and it's fascinating. I love the idea of a little Goldilocks universe where K is Norton, W is mine as well. But I remember a long while ago, going back when Fred Hoyle was poo-pooing this, he had his own theory called steady state.
He did, yeah.
And we never really studied that because it sort of went into hibernation. But wasn't that something to do with the universe was expanding and matter was being created to fill the space?
Yeah.
That sounded a little bit like what you were talking about with the rip, moving towards the rip.
Yeah.
Was there anything in Hoyle's
I don't know
theory?
that anyone's sort of resurrected that idea. I think the evidence that there was a beginning, a Big Bang, from, as I say, the expansion, the cooling, and the abundance of the elements all point to that being, an origin event that we call the Big Bang. And as you say, in Fred Hoyle's steady state universe, he didn't have that. And as the cartoon said, he actually invented the term Big Bang as a derogatory description of it. So quite what he would have made of dark matter and dark energy, I don't know. Yeah, interesting.
Hi, thank you. Really enjoyed the lecture. You didn't mention about inflation theory.
I didn't, yes.
As a prequel to the Big Bang.
Yeah, I mean, the idea is that soon after the Big Bang, after 10 to the minus 35 seconds after the Big Bang, something like that, there was this brief period, lasted for, well, yeah, about 10 to the minus 35 seconds, in which the separation between stuff got immensely bigger. Alan Guth's inflation theory. That's actually what has been used to explain the fact that the universe appears to be flat. The idea is that that inflation sort of smoothed out everything. So any irregularities, departures from flatness are so far removed from us, they're sort of over our horizon in terms of information that could reach us. So yeah, inflation is a key part of the Big Bang, to give this flat universe, to give a universe where the cosmic microwave background is uniform across the sky to within a few parts in 100,000, wherever you look. That homogeneity and isotropy is explained as a consequence of inflation.
The American billion is 9. I mean, this is how it was when I was.
Yeah.
And I always used to have great fun going around saying that British numbers were bigger than American numbers. Any more questions? In which case, I think we'll say thank you very much, Andrew, for a fascinating and entertaining
Thank you very much,
presentation. Yeah. Thank you.
Thanks for all your questions too. Thank you.
Now I'm going to hand back to Alan to finish off.
Right, well, thank you very much indeed for that wonderful talk there, Andy. Thank you for coming down and giving that to us. It was absolutely really enjoyable. We do very much appreciate it. Some of you on Zoom will have heard this before, but I've got to go through it once more. We had a little chat while we were off at the air for a moment. Just to say a very big welcome to all the guests who did come along tonight. If it was from the meeting, my telescope doesn't work. We're really pleased you're following that up. There are some photographs of that event on our website. If you go to the homepage, look at the top, second tab along, it says MTDW, and I think you will find it's really fascinating to have a look at those photographs. And we hope that you'll come to future meetings. Also on the website, there's a little section from Ticket Source who sell the tickets for the events. They're running a community project where they're giving away some money to local communities, and we've made up an event, another My Telescope Doesn't Work event, so that we could enter the competition. To win it, we need a lot of votes. That's all you have to do. Doesn't ask for anything else. So if you can find time to go along there, pop a vote in for us, and get your friends to do it, as many friends as you can. There are some prizes from £1,000 downwards, and we certainly would appreciate a little bit, perhaps towards My Projector Doesn't Work fund. Next month, we want you to come along to our next meeting. That's going to be on May the 10th, when Dr. Oliver Shortall will be coming along and talking about rocky planet atmospheres in the solar system and beyond. So that ought to be a really good follow-up talk to the one that we've had tonight. I think it's going to be a really interesting one as well. Now, another date for your diary is a week after the next meeting. So this is May the 17th. We'll be having our annual general meeting, and that's going to be on Zoom only. So don't go down to the university. It's just going to be on Zoom. We'd like to see lots of you there. You can come along and tell us what we're doing right, and you can tell us what we're doing wrong, what we could do better. That's the only way we're going to find out about things. There is a tab actually on the website that you can submit any ideas for future meetings. Just press on there, put in something that you'd like us to do, and we will do our best to try and find somebody to come along. So all that we need to do now is for me to say thank you to the technical team. It's really hard work. We thought when we moved to the university, things were going to be really easy, that we could use their equipment. Boy, were we wrong on that one. We can use their equipment, but it doesn't seem to work quite as smoothly as we had hoped. But thanks very much indeed to our team down there who put it all together, and to all the rest of the committee who worked so hard to make these events possible. So that's enough from me. I'd like to say thank you to all of you at the university and hope you have a safe journey home. And to all of you who are on Zoom, well, we can continue for a little bit longer. So officially, goodbye. We'll see you next time.